Well, thank you very much. First of all, I would like to thank the organizers for the invitation, in particular also Jane and James for their patience with me. So ultimately I was on a very complicated schedule and somehow we managed to get through it in a sense, so I'm happy to be here. So I also noticed that I'm perhaps a bit more stationary or somehow, let's say, squeezed into dynamic talk. There's another dynamic talk afterwards perhaps, and there's mine in between which is a bit more stationary. So in a sense that I focus on an image, but of course you can imagine that later on you may do something like that for movies as well. And we have heard from Andrew this morning that, well, who wants to tune parameters? I mean, nobody wants to. And I would like to at least give you some idea on how we try to come up with the procedure which automatically chooses certain parameters. Well, we know many of the problems we're dealing with are related to inverse problems, and inverse problems are, of course, notoriously always depending on filtering, regularization in one way or another, and choosing that parameter is very tough. I mean, there are heuristics people have invented which work more or less well. And I would like to find something which is not just scaling a scalar parameter, but even tries to take the regularization parameter as a function. So if you think about an image, well, you have details, you have homogeneous larger regions, and we would like to somehow filter differently in different regions within the image. And this is the talk I'm going to present here. And I would like to start with a little bit of history. So we started out with something which we call spatially adapted total variation. We have seen total variation regularization in Daniel's talk. Which still seems to be useful, although let me mention already here that it's not just limited to total variation, you could do it also for other types of regularization. So what we have in mind is a classical degradation model. You have a true image U hat, which you somehow send to some machine, which distorts it, produces a KFU hat, and then it's transmitted and some sort of or noise is added on top of that, and this gives you ultimately the image data Z here. Well, and then total variation would do the following. You design a filter, or let's say filtering does the following. You would like to minimize the activity of a filter while still preserving certain properties. And the classical view in total variation would be you minimize the total variation of the object you're going to identify from data Z, and you would like to have certain statistical properties satisfied. This is the one which we see more frequently, which is a kind of variance constraint. There's also a mean constraint here, but the mean constraint can be somehow scaled out. This is why you see it only here in light gray. So this is the focus one. We are more frequently used to see the problem in this particular format here, where we somehow intertwine both on one level, and then you may need to choose the lambda here. And there are various guidelines. One guideline could be to say, well, this isn't really an equality, but an inequality. There's a Lagrangian multiplier, which then happens to be non-negative. Why not choose lambda to be the Lagrangian multiplier for the constraint in the constraint formulation? And that's one point of view, and this gives you one reconstruction, which might be more or less the one you like or you don't like. But what we are interested in, as I already announced, is I would like to somehow distribute that weight locally. So I would like to filter in, let's say, homogeneous features as strong as I can, and in local regions as little as I need, because I would like to get, of course, rid of noise, say, while still keeping details. And this is more or less the first part, and I'll be quite quick because this is a bit more historic work. So we would like to choose this ideally automatically, because how can you choose it if it's a distributed quantity manually? So this seems to be somewhat hopeless. There's some literature. I won't go through the details here. If somebody's interested, I'm happy to talk about this. So what we're going to do is, well, we pick up the constraint optimization point of view by doing the following. You design a filter, which is a function which is non-negative on the square of your image domain omega, so it's omega cross omega. It has to be sufficiently regular, so you'll see many function spaces throughout. So, well, we do a lot of work in function spaces and try to be consistent and faithful with that kind of formulation. I won't emphasize those. If somebody's interested, I can also tell you reasons why I would like to analyze things rather in a continuous setting than in a discrete setting. And a lot has to do with mesh independence of solvers. If you refine resolutions of images, how does your solver behave? Does it still converge? Does it get much slower? Does the number of iterations increase, and so on? And there's a lot you can learn by looking at the continuous world here. Okay, so we look at this particular filter. It has to be one in a certain average. It should be non-destructive in that specific sense here. And you may have different choices like mean, Gaussian, Wiener filter, whatever, which you may choose in order to localize your image residual by this particular filter process. So what I do, I would like to know what's going on with the residual at the pixel X. and then I look into its neighborhood according to what the filter does for me. I get back this estimate of this local residual, kind of filtered over the window, and this is now a constraint which is pointless almost everywhere in all of the image domain omega. And I would like to now consider this as my new constraint rather than the one which you have seen over here, where I could have written an inequality as well, but for statistical reasons we know it should rather be satisfied as an equality here. Also, I should have mentioned that sigma square is the variance of the noise. I mean, strictly speaking, there's also in function space, this is not Gaussian noise, because Gaussian noise cannot be square integrable in most of the cases of its realization. Rather, we should think about eta being an oscillatory function with zero mean and a sort of standard quadratic deviation from its mean being less or equal sigma square. That's what you see here. Now, if I localize the constraint, well, then I can replay the game with the Lagrangian multiplier and say, well, this is a constraint now all over omega. There's a Lagrangian multiplier, which is a distributed function, and now replace the lambda by the lambda x, and the x would be a space within omega here. And that's what we did. In practice, then, well, we continue in discrete terms. What you may choose, for instance, is a mean filter, but as I said, there are other filters. You fix a pixel ij, you look at the little window of a certain width around the pixel ij, you average over that window. This gives the quantity s, which you have seen on the previous slide, but now in discrete setting at the pixel ij. And now you have to learn how to properly compute this quantity lambda so that you really have a good local weight. Just a little graphical sketch. Again, at the pixel ij, we take a certain window, we average over that window, but of course we could have different window sizes, different window styles, and things like this in mind, but this is what the mean filter would give you, for instance. And then based on this formulation here, and after some reweighting, you get something, well, and if you would, well, after some reweighting with a sigma square, you get something which almost looks like this. If I would, let's say, plug in the true solution here, then I would have here k of the true solution minus the z. What would remain is just a noise. And if I just look at this quantity here, then I may study its kind of behavior, because this is the ideal quantity. So I would like to filter out everything which is imposed on the image. Again, I should assume k is known to me here. I would like to get rid of all the noise, and so the residual ultimately should only be the noise, because I don't like to have noise inside my residual image. So now I study statistical properties of this quantity, and I try to learn certain sort of confidence bounds for updating my parameter lambda. First observation, this quantity is distributed along the chi-square distribution with as many degrees of freedom as you have pixels in your filter window, with a sort of periodic continuation along the boundary. So brief discussion. So again, let's assume U would be the true information. Then if you take your local variance, as I just discussed it, you get back this quantity with the appropriate weight here. And what you would expect, of course, is the following. That if you don't have the true information, so you have, let's say, an over-smoothed version, so you have too much filtering going on, then you would compute a local residual which is well above this quantity, which would be the quantity related to the ideal reconstruction. And what we did then next was to compute a suitable upper bound in order to decide whenever this S would be sufficiently large or not, because we're working in a discrete setting with different window sizes, and you need to have a reliable bound, because if your window size is bigger, you have a bigger number of points to sample from, so which means your estimate of a variance is going to be more reliable, whereas if you have a smaller window, you have a smaller number of points in that window, and your estimate of a variance will be less reliable, and your bound for making decisions has to somehow take the statistics of your underlying decision process into account. For that, you can come up with statistics of the extremes. So what we did, we computed a bound according to the following. Let's assume you take all your filter windows, and for each center of this window you compute a sort of variance estimate. You take the maximum of all of those and its expected value, again after some reweighting. And then you would like to somehow and then you would like to compute the corresponding bound from that information. Well, for this, obviously, you need to understand how the max of m square, and m square is the number of pixels I have in my domain, random variables which are chi-square distributed, are how this maximum in its own right is distributed. Because once you have the distribution function of the maximum, you can somehow study its further statistical properties like the mean, like the standard deviation. And that can be done. So I think I don't go to the details here, but what you can do is now, by assuming that I don't want to somehow find a reliable bound for every little filter window, because there could be tremendous noise affecting one of those windows, but in average I would like to have that the max over all of those random variables does something good. So you try to identify the cumulative distribution function, or in other words the density of that distribution, and this can be done exactly. So I give you a specific distribution here, so this follows the so-called Gumbel distribution. Looks a bit strange around the dominant value, but the only message is, so the idea is you have a finite number of random variables, you take the maximum and you look at this maximum, and you would like to get the statistical information out of that. You get the density of the distribution, you get expected values which are extremely precise, so there's the Euler-Mascheroni constant here, and you get the standard deviation for that. Okay. And now what you may do, you may say, well, if I have such a random variable and I would like to be less or equal the expectation of this max, and look at the probability, you get a certain probability back by plugging into your cumulative distribution function. If you relax the upper bound, obviously your reliability increases a bit, because you're a bit more generous in a sense, and that's what we would take as an upper bound for our decision process. So what we do, we say, okay, we look at all of those windows. We don't want to ask for each window stay below a bound, but in average we would like to be below the expectation plus the delta. And then you somehow scale your S correspondingly. If you're inside this window here from 0 to B, which is your reliable bound, you would say I did a good filtering job, so there seems to be no information in the residual. I rather would keep the regularization locally at the level as it is. And otherwise, if you exceed the bound, you still have to do some updating of that regularization parameter. And the updating is done here in a very simple, you may call it augmented Lagrangian type fashion, as we've seen it, I think also in Daniel's talk. There was the primal dual algorithm, and the dual update for certain constraints would very much look like this one here. So you have a current estimate, you have a multiplier, lambda. You look at the local residual. If it exceeds your variance, well, there was a rescaling going on. Then you have another contribution here, which you weight by parameter rho, which may be user chosen. And if it's below that bound, you just keep it. So here we now see the sigma square, because there was a rescaling going on in the previous. And then you average in the filter window, and this gives you your lambda. So this would be the corresponding information. And with this, you can set up an algorithm. You choose an initial lambda. Usually what we do is we choose a very small one, which would and a constant one, which would result in overfiltering. So you get back a cartoonish looking image. You solve the reconstruction problem. You look at the local filters. S, you check whether they are above the bound or not. If they're not above the bound, you keep your level of regularization locally. If it's above the bound, you update locally the regularization lambda. And then you repeat this iteration. Well, we have another way of speeding up. I think I don't go into the details. So we do here a hierarchical decomposition. So rather than just updating lambda by this process, we somehow feed back the solution, subtract it from the current data in a sense. So which means in the initial situation, you fix a lambda, you solve the total variation problem, you get the solution, you subtract the solution from the data, you update lambda with the new data, now subtracted by the first initial by the first solution, and you keep on doing this until a certain stopping rule is satisfied. So this is what hierarchical decomposition means here. And what it does for you is the following. So there is the cameraman picture. So you start with a very small initial constant lambda. You get back a cartoonish looking reconstruction. So then you look at the residual image, and this is how it would look. This is how it would look like. You do this local adaptation of the weights lambda. You get new weights. You resolve the image reconstruction problem once again. You look at the residual and you repeat this process, and after 3 steps you get, I would say, a reasonable reconstruction of this process. So each step requires to solve an image processing problem and a way to update your weight lambda locally. And of course solution algorithms and then on and so on, but we have a sort of toolkit for that. And as I said earlier, generalizations are possible. You can use different regularizations like total generalized variations or others. So far so good, and we applied it, and if somebody's interested, you can go to my webpage, download a little MATLAB script, and you can play around with this. What are the limitations? Well, limitations are obviously, a lot of my explanation was related to details in images versus homogeneous features. Now what about operators K which send you into a different space? Sinograms, like in tomography, in radon transform situations in tomography, or Fourier or wavelet coefficients, or similar. So we somehow would like to capture such situations as well. Secondly, well, there was a sort of, I agree also what we've seen before, that the dual usually does a sort of maximization of a dual problem, so which means we may have a way to interpret the update of lambda as sort of maximizing a dual problem, but really it's not quite like this. It looks like a pipeline process. You somehow fix the lambda, you solve your image processing problem, and then you update lambda by some other external mechanism, and we invented one, so to speak. I would like to have everything put ideally into one, call it optimization framework. And the remedy in a sense is now to, rather than looking at lambda, I would like to, we have seen a row of in front of the gradient term in Daniel's talk, I would like to shift the weight from the data fidelity to regularization, and there's an analytical reason why we haven't done this up front, but I don't go into the details again. And we would like to invoke a bilevel framework in order to have everything in one kind of optimization framework. And bilevel optimization has become interesting in image processing recently. So a little shift, which seems just a little shift, if lambda were scalar, then there's obviously nothing different, but in a sense it's just all upon scaling. But if it's distributed function, going from lambda here to alpha there is a long way actually, function analytically. Alpha needs to be rather smooth in order to make sense to being somehow weighted against this object here, which comes from total variation, for instance, and is known to be a measure only. So this is a measure, and for this integration or this pairing to make sense, alpha needs to be a continuous function. So there are some analytical difficulties in order to have everything well posed. And then still I need to tell you a bit about the bilevel frameworks. Okay, so this is step number one. And despite the difficulties, you can prove that if alpha is a uniformly positive function and k is not too bad, so it doesn't annihilate constants, then you still get existence of a solution. So in a sense, the parameter to reconstruction mapping is well defined. So if I feed the method with an alpha, it gives me back a u of alpha, and I can somehow analyze this mapping here, because that's important if you would like to do some adjustment later on. An alternative way of looking at this problem, or the total variation we've seen earlier along, is to look at the dual problem, which you can see here, or strictly speaking, a pre-dual problem. So what you do is you have a concept in optimization which is called Fenchel dualization, and after some work you can find out that the Fenchel pre-dual problem of this is this specific problem here. I stress the fact pre-dual because in function space, total variation, the space of functions of bounded variation is a non-reflexive Banach space. So if you dualize and dualize again, you do not end up in the primal space where you started out front originally, but usually you end up in a larger space. But it turns out if you look at this problem and dualize it, then you end up with this total variation problem. And this is why I emphasize the pre-dualization. And the other aspect here is there's a space. I mean, if you know it, well, fine. If you don't, well, doesn't matter. But the interesting fact is this is a Hilbert space versus this is a non-reflexive Banach space. And from an optimization and mathematical point of view, doing numerics in non-reflexive Banach spaces is a bit more cumbersome versus doing numerics in Hilbert space. I mean, after discretization, this distinction gets lost, obviously. But in function space, there's quite a difference here. Okay, so that's what we're looking at. So now we have to find a dual quantity P, and once I have the P, I can reconstruct the U from P by a well-defined process, actually. Now, what is the bilevel concept now? So let's assume the following. We have decided on an alpha, we solve the total variation in its pre-dual form. You get back a P, and I give you a recipe how to construct the U. Well, we are done. But let's assume I don't give you the right alpha. Then you may say, I have a sort of objective, or I have a goal which I would like to optimize, minimize, or achieve. which depends on my choice alpha and on my reconstruction P, or in other words on the image U. And I would like to adjust alpha in such a way that this upper level objective gets minimal. Alpha has to satisfy constraints, can't become 0, can't become ultra large, and P has to solve the total variation problem or its pre-dual form. So this is not bilevel, and in economics you may say it's a leader-follower principle, because the leading quantity is the regularization parameter. Once it is fixed, the reconstruction just follows as a solution process. So alpha leads the P in a sense, and this is what I would call a leader-follower principle. So we need to fix the choice of the upper level objective, because we can't do choices which would insert knowledge of the true solution, because that would be convenient but infeasible. Well, admissible set for alpha is simple, just lower and upper bounds. And then the trouble is we have to talk about this optimization problem, which is terribly complicated from a theoretical point of view, because it turns out that this constraint gives you degenerate constraints and you need to handle them in a proper way. Now what about the objective? Well, let's just jump down here. So what we do is the following. Well, let's look at this one. So this is the dual version of the localization of the residual. So in the first part of the talk you've seen the classical ku minus z being localized. If you transfer it into the language of the dual variable, this is what it looks like, and the w is just as a filter as it was before, and this is now a localization of this residual, but now written in the dual variables. And now we define a so-called variance corridor. So we fix, depending on the statistics, I don't give you the formulas here, an upper bound and a lower bound, and we are happy if we select the P, which gives us localized residuals falling into that corridor. And this is now the objective. We would like to find alpha such that the reconstruction P associated with that alpha falls into our variance-based corridor, which is based on the statistics for the choices of epsilon or the upper and the lower bound. You may also introduce some additional weighting functions, which we don't actually. We just do one in both cases, but you may be a bit more general. Now we have a very specific optimization problem with that objective, with the pre-dual constraint and some further constraints sitting down here. And then you have to discuss the usual things. Well, does there exist a solution? Yes, there does. But the design of solution algorithm is a big challenge, because it turns out total variation is non-smooth. Well, let me just go back. This is not really non-smooth, this is quadratic, but the non-smoothness sits here in the constraints. An inequality constraint is always a sort of inherent non-smoothness, which causes some troubles when then analyzing this optimization problem and designing solution algorithms. But nevertheless, you can go through this, so I don't go through all the details. So, well, you can fix the sensitivity of P, but not differentiability properties. Okay. You can somehow fix the difficulty with lambda, that it has to be smooth, by a simple, very weak additional regularization. So alpha just has to be a continuous function. Continuous functions are not necessarily H1. And so we do a very weak regularization, but can show that this is fine. You write down first order conditions. I don't go into the details again, but that there's a mechanism for doing this. And then you may want to study certain parameter dependencies, which are partly still open questions here. I would rather like to jump forward to the numerical solutions that we have, so you can study further properties. As I said, you have this alpha, which can be dealt with by a projection process, which gives you the regularity you need in order to have alpha in front of the measure, which comes from total variation. And in essence, it's a continuous function. That's what you're going to need. Now, numerical results. A very simple test. Well, we all know that little corners are usually cut off by total variation, because its nature is, in this binary context, to round off edges, because it's related to the perimeter of features. Now, if you look into the details, well, this is what the classical total variation would give you, and this is what the spatial adaptive weight gives you if you zoom into the pixel level. So it turns out that even down to the pixel level, it seems you're not cutting off corners as total variation would do for you. And if you look at the PSNR or the structural similarity indices, you see how this behaves over the iterations. So each of the boxes is an alpha update. So you see, you start with a low PSNR, then you update alpha by a bilevel iteration process. You update, and you're improving, and most of the improvement is done in these corner regions here. And this is by appropriately choosing the regularization parameter. Well, how does it look like? Well, this is the alpha. As you see, the alpha pinpoints the corners of the triangle because that's where it needs to do little regularization, because if it's strong there, we are cutting features. So fine features are lost if you have lots of regularization there. And this is just a gradient image, but this is perhaps the more interesting one. This is the alpha function where you can see that it primarily focuses on these regions here. For the cameraman, again, noisy image. If you look at best possible scalar, which is done well by a PhD student according to PSNR, MSSIM, and according to his eyesight. And then you compare this earlier version of the method, which I've shown in the first part, versus the new version of the method, you see a certain difference, and this is the corresponding spatially variant automatically chosen regularization weight, which you can see here again as a sort of movie how it behaves over the iterations. So you start with 1 and you see that the tripod gets in a sense sharper and sharper by finding the appropriate weights over the iterations automatically. So there is no user interaction in a sense, you just specify a constant which gives you a cartoonish image up front, and then you automatically detect this regularization weight. You can do it with deblurring. That's the corresponding weight which you get for deblurring, known operator K. This would be for wavelet inpainting, where 60% of the coefficients are maintained, 40% are lost. This is the corresponding alpha, which is automatically detected here. This would be best scalar regularization. This is, again, bilevel optimization regularization. You notice the difference. We did it also for medical images, where you always can see the original image, the restoration, and the features of the corresponding regularization weight alpha. And with this, I think I have taken up my time, and thank you for your attention.